Alright, here's another good one from the Serway and Jewett text, which you can find for free, I believe. It's 8th edition. But I like the examples in it, so here we go. We got one block in contact with another block, and mass 1 is greater than mass 2. And a force is pushing to the right there, in the horizontal direction. It is a constant horizontal force, and we're just going to label it F. We're going to use M1 and M2, and we'll leave this in terms of F, M1, M2, and gravity and acceleration. Okay, so what we should do first is look at free body diagrams of each of these. So, free body diagram on 1, and then a free body diagram on 2. Should always be your first step if you have forces involved. Well, if I had mass 1 right here, that's our mass center. We know that some force is applied to the right, so we can put that over here starting from the mass center. You could have put it coming in this way if you wanted. Same thing, but here we have some force applied. We always have some weight mg pointed down, and that means we would also, since it's sitting on a table, have some normal force. We'll call it the normal force on 1. In this case, because it's a flat surface, these normal force will equal the weight. I'm going to leave one force out and then move on to free body 2 right now, and then we'll come back. So if I draw free body 2, it's a little less massive. They represent that by being smaller. That doesn't mean it's less massive, though. We have mass 2 times gravity pointed down, and we have a normal force on 2 pointed up. What else do we have? Well, we have action-reaction forces. One block is pushing the other block. So if I called this the force of 1 onto 2, then this would be minus F2 onto 1. And we can draw that like this. Some of this force is going to be pushing on the block. We can call that force 1 onto 2. And some of this block is going to be pushing back this way onto the first block. So force 2 onto 1. I should have drawn them equal length because they are equal, just opposite directions. Okay, now we can apply Newton's laws. There's nothing but a normal force and a weight pointed down, so all we can gain from looking in the y direction would be summing the forces in the y would be, let's just choose mass 1 for an example. Mass 1 times the acceleration of 1 in the y direction. We have a normal force on 1 pointed up. We have m1g pointed down, and this m1 times the acceleration in the y direction goes to 0. All we do is find out that the normal force is equal to the weight. So we might need that. We're going to need that when we have friction. If these two blocks had friction, the more massive block would have more friction, right? I showed you last time quickly that the frictional force is related to the normal force directly by a coefficient of friction, and the more normal force, the more massive an object is, the more friction that will be exerted on it. But what we can do is sum the forces in the x direction on each. That would give us two equations, and what we'd find out is that these two things are equal. And we wouldn't find it out, we'd use Newton's third law, right? So these are equal by Newton's third law. And it ends up canceling each other out. So what we can do is, look at the system as a whole. Pretend these things are glued together. And we can say that some force is being applied, and it's going to move off with some mass times acceleration equal to, in this case, m1 plus m2. So the combined masses. So let's do that. I'm going to sum the forces in the x direction. That's going to be equal to the mass times the acceleration in the x direction. If I look at the forces and ignore the ones that would cancel if we were to make equations from each, and try that out. Make an equation for each and then set them equal to each other, and you find out they go away. So what we're going to do is call this mass m1 plus m2 times the acceleration in the x direction, because they're both going to move with the same acceleration. And then all we have on the left hand side is the applied force. We can rearrange this for the acceleration to get that the acceleration is equal to the force over the combined mass. So very similar to the relationship for acceleration, where our original definition was the force over the mass. Well, it just was a combined mass in this case. The trickier part would be finding the acceleration if there's friction, because each block would have different levels of friction affecting it. And I will go over that. We're just not worrying about the frictional force on this test yet. We'll get right into that after the test. So another interesting thing would be what is the force between them? What's the contact force? What's the magnitude? We could look for F1 onto 2, or we could look for F2 onto 1. And I'm going to do one of these. I recommend you try finding this. You should find out that they're the same thing. Okay, well, if I look at just mass 2, we had, I'm going to go ahead and draw a free body diagram again. Mass 2 had m2g pointed down, the normal force on 2 pointed up. There's no motion in those directions, so they don't matter. Just putting the practice out there. Then we had a force from 1 onto 2. So if I sum the forces in the x direction on this, it's going to be equal to mass 2 times the acceleration of 2. Or we found that they had the same acceleration, actually. The only force is the force 1 onto 2 acting on this mass, the small mass. And we can say that's equal to m2, and then put our equation for acceleration in here. It's equal to the big force applied over the combined mass. Ta-da! That's our answer. So if you did this for the other mass, you would get the same answer, because Newton's third law. So like I said before, it's Newton's third law is something you must know and must be able to identify and regurgitate, but it's not an equation that we will just automatically apply. It's more of something that we'll use to analyze the problem, to make sense of the problem. And same with Newton's first law. If we just need to know that if something is moving, it's going to stay moving in that direction without accelerating. And if it's not moving, it's going to stay not moving or have no acceleration also. Alrighty.